So think about this for a second. That huge question, maybe the biggest question, where did life come from? Was it just some, I don't know, cosmic accident here on Earth? A total one-off?
Or perhaps is it something that happens fairly readily, when the conditions are basically right?
Exactly. And that whole area is just buzzing right now.
Yeah.
Today we're going to dive into some, well, pretty fascinating new research suggesting life might actually get going surprisingly fast on planets like ours.
We're centering this on a really interesting paper. It's by astronomer David Kipping, published in Astrobiology. It gives a fresh look at the timeline for early life here and what that could potentially signal about life, out there.
Right. So our mission today really is to unpack the evidence for this idea, this rapid abiogenesis.
Which is just the science term for life popping up from non-living chemicals.
Got it. So we want to understand that evidence and then think about what it means for finding life elsewhere.
Yeah.
But, and this is the big but we have to remember.
We're working with a sample size of 1. Just Earth. That's a huge caveat we need to keep in mind throughout.
Okay, so abiogenesis. It sounds complex, but it's really about that incredible first step, isn't it? How everything got started.
Absolutely. Imagine early Earth, just a mix of chemicals, oceans, rocks. And somehow, these non-living components organize themselves. It's the origin event, forming that first self-replicating cell. It's truly mind-boggling when you stop and think about it.
It really is. And figuring out when this happened, I mean, given we're talking billions of years ago on a very chaotic young planet, that must be incredibly tough.
Oh, definitely. Early Earth wasn't a quiet place. Constant meteorite impacts, massive volcanic activity, geological shifts. Finding pristine evidence from that era is extraordinarily difficult.
But the clues we do have, they seem to keep pushing that date further and further back, right?
That's the trend, yes. The evidence points earlier and earlier.
Like those potential filaments in Canada. What was it? Possibly 4.28 billion years ago? That's astonishing.
It is. And then you have isotopic signatures in Australian rocks, pointing to life around 4.1 billion years ago.
And the stromatolites, those fossilized microbe mats, they're, 3.7 billion years old?
Correct. And what really stands out, as you said, is how close these dates are to when Earth itself formed and cooled enough to potentially support life. Maybe just a few 100 million years after the planet became habitable.
It really suggests, a quick start, not a long, slow simmer, maybe?
It hints strongly in that direction. And to understand this better, scientists talk about LUCA.
LUCA, last Universal Common Ancestor.
Right. So the idea is that all life today, bacteria, archaea, us, we all trace back to this single ancestral population or organism type.
Precisely. It's the hypothetical root of the tree of life as we know it.
And the timing for LUCA, where does that fit in?
Well, estimates vary, but generally it's placed at least 3.6 billion years ago. But some newer research, which is quite relevant here, pushes it potentially much further back, maybe even 4.3 or 4.2 billion years ago.
Wow. So practically right after Earth formed. How do they even estimate that? It comes down to genetics, largely. By comparing the core genetic machinery shared by all life forms, scientists can work backwards, like constructing a family tree, to estimate when that common ancestor likely lived.
Okay, so you've got early physical evidence, isotopic signatures, and now these genetic estimates for LUCA all pointing way back. And this forms a backdrop for David Kipping's new analysis.
Exactly. His paper, Strong Evidence That Abiogenesis is a Rapid Process on Earth Analogs, really builds on this converging evidence.
The title doesn't exactly bury the lead, does it? Strong evidence.
No, it's quite direct. And he makes this key statement, let me quote it. For the first time, we have formally strong evidence that favors the hypothesis that life rapidly emerges in Earth-like conditions.
Formally strong evidence. That sounds significant, more than just suggestive.
It is. He's arguing the data has crossed a statistical threshold. It implies that, based on what we see on Earth, the default state might be for life to get started quite quickly, relatively speaking, once conditions allow. This has some really profound implications.
Okay, but here's the thing that always gets me. Life starts early, great. But then, complex life, intelligent life, us. That took billions of years. Doesn't that seem, contradictory?
It feels at a tension, right? A quick start, but then a very, very long development time.
Yeah. Like the starting gun went off fast, but the marathon to intelligence took almost the entire race time available.
That's a really important piece of the puzzle, and Kipping tackles it directly. He brings up the finite lifespan of Earth's biosphere. Our planet won't be habitable forever.
Right. The sun gets hotter, eventually boils the oceans.
Yeah.
We've got maybe, another billion years or so of Good conditions left? Less.
Roughly maybe 900 million years, give or take. The total habitable window is maybe 5 to 6 billion years.
Yeah.
So Kipping's point is, if intelligent life does take something like 4 billion years to evolve, as it did here,
then you absolutely need that early start for life itself. Otherwise, the clock runs out before intelligence even gets a chance to emerge.
Precisely. That rapid abiogenesis might be a necessary precondition for the eventual emergence of observers like us, given the planetary time constraints.
Okay, that makes sense. But it also brings up this tricky philosophical idea, the weak anthropic principle. How does that fit in?
Right, the anthropic principle. In its weak form, introduced by Brandon Carter, it basically says that what we observe about the universe must be compatible with our own existence as observers within it.
Because if it weren't compatible, we wouldn't be here to observe it.
Exactly. So in this context, it raises a critical question about bias. Are we only observing early abiogenesis on Earth? Because if life had started much later, intelligent observers like us simply wouldn't have had time to evolve before Earth became uninhabitable.
So our very existence might be filtering our view, making rapid abiogenesis look like the norm when maybe it isn't. That's a tough one.
It's a potential observational bias we have to consider, and that's where Kipping's statistical approach comes in. He uses Bayesian analysis.
Okay, Bayesian. That's about updating probabilities as you get new evidence, right?
That's the core idea. You start with some prior assumption, and then you rigorously update how likely your hypothesis is as new data comes in. Kipping had done earlier work using this method.
Right, you mentioned odds like 3.1 or 9.1 favoring a rapid start based on older evidence?
Yes, using things like the age of microfossils or carbon isotope ratios. Those odds were suggestive, leaning towards rapid abiogenesis, but they didn't cross the conventional threshold for strong evidence, which is often taken as odds of 10.1 or greater.
Ah, okay. So suggestive, but not quite compelling statistically. And this is where the new, potentially much older date for LUCA comes in, that 4.2 billion year estimate.
That's the key piece of new evidence he incorporates. And when he plugs that potential 4.2 billion year age for LUCA into his Bayesian framework, the odds jump significantly.
How significantly?
He states, and again I'll quote, "However, the recent result of a 4.2 Gia LUCA pushes the odds over the threshold for the first time, nominally 13.1.
13 to 1. So well past that 10.1 mark for strong evidence.
Exactly. Based on this analysis, incorporating that potentially very early LUCA, the evidence now strongly favors the hypothesis that life gets going quickly on Earth-like worlds. For every one scenario where it's slow, there are 13 where it's fast, according to this model.
That's a pretty powerful statistical argument. Does it depend heavily on, say, knowing exactly how long Earth will remain habitable?
Interestingly, his analysis suggests the conclusion is fairly robust. It doesn't seem to be super sensitive to the precise total lifespan of the biosphere. He even ran scenarios considering more speculative ideas.
Like what?
Like the Silurian hypothesis, the idea of looking for evidence of a potential pre-human industrial civilization millions of years ago. Even accounting for possibilities like that, the odds for rapid abiogenesis still stayed above 10.1 in his analysis.
So he's trying to make the case robust against various uncertainties. But he still includes caveats, I assume. It's not case closed.
Absolutely not. He's very clear on the limitations. Firstly, that 4.2 billion year date for LUCA is still relatively new and needs more scientific scrutiny and independent confirmation. That's a big one.
Okay, fair enough. Why not?
He also stresses, very importantly, that even if abiogenesis is rapid here, it doesn't automatically mean life is common everywhere.
Right, because the conditions needed for life, those Earth-like conditions, might themselves be incredibly rare in the universe.
Precisely. Rapid start under the right conditions doesn't tell you how often those right conditions actually occur.
Which slams us right back into that fundamental wall, doesn't it?
Yeah.
The end of one problem. We only have Earth.
It's the elephant in the astrobiology room. We're trying to deduce universal rules from a single example. It's like, as you said, trying to figure out the rules of chess by watching just one opening move.
Yeah. Finding life anywhere else, Mars, Enceladus, an exoplanet, even simple microbial life, that would be utterly transformative.
It would be revolutionary. It would give us that second data point, allowing us to start making much stronger inferences about how common and how fast life might be.
And Kipping acknowledges this directly in his conclusion, right?
Yes. He wraps it up by stating, "Our result does not establish that life is common, since Earth's conditions could be incredibly rare," and then points to the next step. Our next task is clearly to look out and address this question. How common are conditions analogous to those of Earth?
So find more potentially habitable worlds and ideally find life on one of them.
That's the ultimate goal. This work strengthens the case that if you find an Earth-like world, life might have gotten started there relatively easily and quickly, but the if you find one and how common are their parts are still huge unknowns.
Okay, so let's try and wrap this up, this deep dive into Kipping's work. It really presents a compelling, statistically grounded argument now for the idea that life's origin on Earth wasn't some long, drawn-out process, but actually happened quite rapidly once conditions allowed.
Mm-hmm. The evidence, especially with the potential early date for LUCA, points strongly in that direction, reaching that formal strong evidence threshold.
Which is exciting. But, and it's a crucial but, this doesn't mean the galaxy is necessarily filled with advanced civilizations or even simple life. The specific conditions Earth offered might still be exceptionally unusual.
Exactly. The rarity of Earth-like conditions remains a huge open question.
So here's something to leave you thinking about. If life does tend to spark quickly under the right conditions, how does that change the odds in the search for extraterrestrial life? Does that quick start make life more probable overall?
Or is the real bottleneck not starting life, but the incredibly long, complex journey from that first simple cell to something complex, maybe even intelligent? Does the quick start matter less than the billions of years of subsequent evolution needed?
Right. Is the starting line easy to cross, but the finish line almost impossibly far away? It's definitely a lot to think about as we keep looking out into the cosmos.